In this work, we study the camera localization problem. Given a query image, compute the 3D position and orientation of the camera within the pre-computed 3D map. There are various ways to solve this problem. We will discuss two main categories: the retrieval-based methods and the learned methods that includes absolute pose regression and dense scene coordinate regressions. Retrieval-based methods takes as input a query image and find the top case similar images from the database to perform 2D to 2D feature matching and obtain a set of 2D to 3D correspondences. The camera pose can then be obtained using a pose solver. The retrieval-based method, despite its high accuracy, requires a large amount of 2D feature descriptor storage that can be used to reconstruct image and thus is not privacy preserving. Fortunately, this limitation can be addressed using learned camera localization method. For example, absolute pose regression estimates the camera pose directly from query image using CNN. This approach is fast and simple. Its accuracy, though, is low. Scene coordinate regression estimated 3D dense scene coordinate to establish 2D to 3D correspondences. Then the camera pose is estimated using a pose solver. Though this class of method has higher accuracy than absolute pose regression, memorizing 3D scene coordinate from 2D image is a highly used pose problem that makes the learning difficult. Our main idea is to designate a sparse set of 3D scene landmarks that can be easily recognized in an image. For example, we show here the correspondence between a 3D landmark and its projection on the image. Once we establish the 2D to 3D correspondences, the camera pose can be estimated. Here is how our scene landmark detection works. Each distinct color blob represents a learned 3D scene landmark. Like scene coordinate regression, our scene landmark detection also estimates 2D to 3D correspondences and uses a pose solver to obtain RNT. In contrast to scene coordinate regression, our method learns to predict 2D location of a predefined scene landmark, while scene coordinate regression learns to predict a 3D quantity such as scene coordinate. We argue that our representation is more suitable for camera localization. SLD takes the input a query image and predict a heat map for each scene landmark. We use a dilated convolution neural network with a ResNet-18 backbone and 4 dilated rates. To improve the resolution of the heat map, we use a transport convolution layer. We train the SLD network with the MSE pixel loss with data augmentation. During the training of SLD, we select a set of landmarks denoted as red from the SFM point cloud that ensures a sufficient coverage of the scene. We show a few examples of selected landmark patches. However, there are many cases when the number of visible landmarks are not sufficient for the pose solver. We propose a neural bearing estimator that directly predicts the bearing vector toward all designated scene landmarks, including the invisible one. The camera pose RNT is obtained by using the pose solver on the combined 2D to 3D correspondences from both SLD and NBE. The implementation of the NBE are detailed in our paper. To show the effectiveness of our method on learning large variability scene appearance, we present the Indoor 6 dataset comprising multiple captures of the same scene at different days and at different times of the day, as shown in this example. Each scene represents an indoor environment ranging from the apartment to house size that we can obtain a full structure from motion point cloud. We present the quantitative results on the Indoor 6 datasets on the 5 degree and 5 centimeter metrics. For methods that only require storing a neural network, our NBE plus SLD achieve the best performance. Moreover, the efficient version of our method also outperforms state-of-the-art DSAC-star. Although we underperform H-log, but if we restrict the number of landmarks being used to 300 or even 1000, our approach outperforms H-log. In conclusion, we present a new learned camera localization method that predicts predetermined scene landmarks in images. Our method requires low storage, is privacy preserving, and is high accuracy. Our code and dataset are publicly available.